I'm going to welcome you all here to this webinar today on concrete design. It's a bit of a mixture of different things, and we will see why in a moment. So if I was just to start and go on to the next page, so as a recap, product range of MasterSeries. We have a vast range of different programs that are available to you to do different things. They're all individual modules. You can purchase those individually, or we like to bundle them into different suites. So we have the big building design suite, and we have the power pad plus the portals, and then the custom suite. We're probably going to look a bit at mostly inside the building design suite, but a lot of it will refer also to power pad as well. So if we look at what's in the building design suite, we'll be doing frame analysis, absolutely. We'll even do some wind analysis, and we'll pull things in from from Revit. In fact, in this case, we're going to pull a Revit file in and look at that. We're then going to create FE elements. We won't be doing any dynamic or seismic. It's not sensitive. And we can do steel or concrete design composite connections. Today we'll be looking at the concrete and the concrete slab. So what we're going to be looking at today are the two concrete components, the finite elements, the frame analysis, and a wee bit of wind and the BIM integration. So those are the different aspects that we will be looking at. So hopefully you can all hear me now. Somebody is saying, Omar, you can't hear me. I am talking and I believe everybody can hear me. People have just put up their hands to say yes, they can hear me. So that all sounds good to me. I'm going to just do a wee quick check here. Yep, and I'm speaking, I'm live, and everything else is good. So any questions, please type them into your little question box, and my colleague Andreas Herbe will answer your questions, or leave them for me to go over at the end of the session. If you cannot hear me or not getting a good sound, in the UK you might consider switching from phone to VoIP, or vice versa, to just switch and marry. The other option is to come back in again, to exit and rejoin the session. So we're going to look at the building design suite today. So I'm just going to close all that down, and we're going to go straight into Revit structure. And here's a nice frame that we've got, and we'll see all the different members. And what I'm going to do, just to make my life fun, is going to take that member and I'm going to move it. Hopefully I can move it. Can I move it? Not certain if I'm in the right window. Revit's not one of my expertises, and I usually can move things. There we go. We're going to move it over here. So now just move that column out of the way of the other columns, just to prove that this thing is live, and it was a weird dimension. So to get this from Revit into the MasterSeries, it's a very straightforward process. We have an add-in called MasterSeries Link Manager, and we're going to go and we're going to remove any existing links, and we're going to create a brand new link. And I'm going to put it into my temp directory, and I'm going to call it conc model. And the time is 1306, so 1306 is the reference, just to prove that it's unique, and save that. So now I'm going to save all that, and I'm going to submit this for the first time out to the repository, the intermediate file that hooks between the two systems. So that's my building. I'm now going to minimize this down and come into the MasterSeries. So in my case, I'm going to go and I am going to import a Revit link, and it has just put it on the other screen. I'm just going to pull that across. Here we go. And we're going to connect to an existing link and into temp, and it'll see the new one called 1306. I'm going to open that one, and I am going to create a new model from the link, a brand new model, and it's also going to be called 13061. Must have put a 1 in the front there, didn't realize that. And I'm going to import slabs as FEs, walls as FEs, retain the coordinates, and it's going to be a master frame file, and extract. So off it's gone, and it's built all the members, and I'm now going to open that file. And here we come, nice little wireframe. If I turn on 3D, you'll see that we have slabs. You'll also notice that the first floor, the roof, was not an FE surface. It was simple beams with slab spanning. And here's my column that's in the wrong place. So what I'm now going to do is I'm going to try and move that back into position. So I am going to go to create, modify, Tommy, modify, move, and I'm going to move that member and all of these ends, and I'm going to move them, turn off the 3D for a second, so that hits that. Very straightforward. So I want to move it so that that point hits that point, preview, looks good to me, and apply. And while I'm at it, I might as well just change a property. So properties and section materials, and just look at my upper columns here. Here they are, the 400 square. I'm going to reduce that down to 350 square, and I'm going to copy that onto that one, and that one, and that one as well, and inside the frame the back 3 as well. So these 6 columns are now changed, and I can go through and make any changes I want. I can go through, do my full design, and then, having done my design, send those redesigned sections back. Normally the section sizes don't change as much as they would in the steel design, the gross sections. But if I want to now, I can go to BIM Exchange, and I can, in the Revit Link Manager, and again it's on the wrong screen, I want to submit changes to the link. So that should have submitted changes to the link. And if I come back in here, what we're going to find is if I go to Link Manager and I want to update the model from the link, let's move away, update the model, and it's found that these have gone from 450s to 350s. And the reason we give you this auditing is because even if you have changed it inside Revit or your detailer, in the meantime, or the architect, it'll also tell you that the original was this, you've changed it, and the drawing has this size as well, and you can then choose what you want. We're just going to say update the section on all of those, and you'll see the coordinates have shifted for those beams and column, and I'm going to say okay, yeah, go ahead, and it's now going to update this model for us. And it's saying yep, and I can say close, and we'll now see the smaller columns above, and this one is now back in line with where it was. And if we'd added any additional sections, those will be the same. So we have this full round trip integration, and I could now come and make another change and send it back into the same master frame model. If I said no, I want those to be 450s, I could do so, but I'm not going to do that, because what I'm going to do, and I'm going to save this, yes, what I'm going to do is I'm going to look at this model. I'm going to play around with one or two things. We're going to look at how we create an FE surface. We're going to create this roof FE surface for you. So let's go in and create an FE surface. And I'm going to create a brand new surface. And I am going to auto select. So I'm going to put this into front view. And I'm just going to go and do that. Sorry, I need to be in apply mode. Do that. And now what I've got is this model. And even though it's showing the internal members, those members don't count. So if I then move to another surface and back again, you'll see that it only has that member. Now if you remember, we actually had some nasty openings in here. So we can come along quite simply and go down to openings, and I can say I want to auto pick the openings, and I'm guessing the openings there, and it's taking these three and it's not quite right, so I'm going to say right, let's not auto pick. I was looking with members at the wrong elevations, and I believe always the danger of not looking in the one plane. Take all those out and then just go into front view. Do I have views? I have a ground, level 1 and roof. So we're on roof and we're now looking at this, and if I put this into top view, it's actually killed all the other members because they're no longer part of that arrangement, and I could go in and create members to add those in. What I'm going to do is I'm not going to work with this model. It's quite a large model and we don't have enough time to do everything inside the hour, otherwise we'd all be making an absolutely massive fortune if we could do buildings of that size in an hour. I'm going to pull in something that I've put together. Some of you might have seen some of it from before. I make no apologies. This is a model that we've done previously. I've tweaked it, and how have I tweaked it? So let's turn on the 3D. I have stuck a little plant portal frame in the top. Why not? Because I could, because we can in steelwork. I've made some openings with upstands around here. I have put some downstand beams around the perimeters of both these ground and first floors. And why have I got ground floor slabs in my model? Well, simply, this half is on a piled foundation. So it's a suspended slab on piles. And even worse, this half here is on a raft. So we are getting some quite interesting things. What we also have here is, I notice that this column is quite large, and I might reduce that down in size in a minute. We have a single column in the middle of this floor coming down onto the slab, but below we have two columns, so we have a transfer slab scenario. Likewise, this portal, to a lesser extent, will be a transfer slab. So I'm going to go, first of all, I'm going to change those two sections. I just don't like the size of those. Properties, section materials. What's that one? And I'm going to do global. It'll take its brother at the same time. It's a 400 by 700. That's quite big. Let's make it 400 by 400 square, or 400 by 450 square. Let's make it 400. Okay. So it's now in the same category as these other members. Very straightforward. The other thing I notice is my slab here and here appear to be two different thicknesses because somebody was playing around. So let's go and look at a slab. Slab properties. So first of all, let's look at how you create a slab. Edit slab. You saw how I created the boundary of the slab in that previous example, so I'll not do that again. And we're going to look at this slab. So what this slab has is it has no openings, it has no edge supports, it has no attached beams, and it has a material thickness. So what's the material thickness? Well, I think over here we allowed 200, so we might as well go for 200 here. Although it could be fun around that there, but I'm going to go for 200. And we're going to use a codified material C2530, which will allow us to do our accurate slab design afterwards. The loading is very straightforward. It is a 2.5 kilonewton live load. And there's no other loads. There's no walls. The self-weight of the slab is included. If I wanted to put some asphalt over the top or something, I can include that as an additional dead load. So let's do that. Add a load. And I'm going to go for a dead load of -1, and it will be a dead alternate. And you might ask why the dead alternate, and we can explain that better when we get to somewhere like here. So if we come in here, and we're going to also add in another load, that will be a dead load, and -1. So in here I've got quite a few loads. Just pull that across. In fact, let us just go into our view filters and look at the level 2. No, it's level 3 roof as it sees it. So there we are. There's our roof. So what are our loads? Let's get back to the start. The live load, a patch load, which is additional. So 2.5 live, and then 5 additional inside that plant room, which is going to give you 7.5 or thereabouts. We then have a couple of perimeter loads around these openings, because there will be some sort of glazed item over that, and we've just put 2 on each dead and live, and then we have this additional line load. So very straightforward, very easy to apply. The openings again are very straightforward. The one thing we haven't talked about here is very interesting, is that when we're looking at our slabs, when we're dealing with our deflection loading cases, then we want to take a weaker material to allow for creep and to allow for cracking. And we use the Concrete Society guide, which allows us to say whether or not we want cracked short term, cracked long term, which is really for storage, or just cracked where you're not that worried. We're going to go for cracked short term creep. That means that every loading case where we have serviceability, it will use this weaker stiffness of the slabs. And of course we do that on the slabs, but we wouldn't do that on the walls or on the columns. So that is your FE loading. Now, I mentioned we have this alternate loading here. And one of the things we have to understand, if I come down to the next level and look at the loading in that, if I was to apply the dead and live load onto all the whole slab in one go, you wouldn't get the maximum sagging here, because this is going to hold it up. And likewise, you wouldn't get the maximum sagging here, because this is going to hold it up. So we need to do a pattern loading. And we need to do that pattern loading in 2 directions. And we do that very straightforward using something called the alternate load patterns. So very quickly, pattern 1 is here. So that means that anything that's inside those slabs, if I turn on my load values D1 and L1, it will then activate them. And to complement that, I then have its brother, pattern 2, that complements that. So that allows me to go max, min, and obviously min, max, and get the patterns I want. But that's only in one direction. What we now need to think about as well is pattern 3 and 4. So max, min. Now this is a wee bit tricky in here, but we're really after the sagging moments in the panel, so it's really critical to understand what happens in here rather than in this little corner here, because this is really going to be governed by this expanse. So the patterns, you can go overboard, but you don't always have to. And likewise in the other direction, it's why we drop down to the columns and back again. So that is going to allow us to have a pattern loading, but that's only half of that battle. If I go back out to full view, I need to create my loading cases. So loading cases. And what I've got is I've got all spans loaded, 1 and 2, and then alternate spans 1, so maximum on the D1L1s, minimum on the D2L2s. And then we have the alternate 2, which is minimum, maximum. And then we have the serviceability of those 3. And then we look at the opposite direction, the 3s and 4s, and do that. So if we take, for example, that one, and look at the loading combination, we're taking our default plus maximum on the D1L1s and minimum on the D2L2s. Now obviously in the Eurocode we don't pattern down the slab self-weights, so we just put the value the same in both cases, and then when you go to pattern 3 you'll see that that's switched around 1.5, 1.4s. And we have all of those, and I have also put in a few wind loads as well. I'm going to put in my W1 here, and it's going to be, I put it in as 1.5. At the same time, doesn't really matter, it's insignificant. And then the W2 direction 1.5. So that'll allow for the wee bit of wind loading I played around with and put on the roof. Now wind loadings are again quite interesting, because what we do is we do two things, and I'm first of all going to turn off this colouring because I want to see them all the same colour. It just makes my life a wee bit easier. That should update that. Well, not to worry, we'll continue. So looking at our wind loading on our structure, we're now looking at the wind directions. So I'm only going to take two directions, 0 and 90 degrees. In plan, 0 and 90 degrees. I'm not interested in anything else. I just want to put a couple on for the fun of it. What I am interested in is the wind application. So the wind location is going to be, I think I went up near probably Isla, one of the islands off, or what's that island off the coast of Scotland, up there. Pass, can't remember, but it's up there anyway. And so we're taking a reasonably high wind pressure up there. We're actually ending up with wind pressures of around 1600 to 8 kilonewtons per meter square. We're going off on that. So that's the wind pressures. The most important thing then is the wind surfaces. So let's look at the wind surfaces. Very simply, we can see then for each surface we've created how we want to apply the loading, and horizontally and horizontally, and apply that very simply onto the structure. It's not a wind analysis webinar, so we will just very quickly say, well, if we look at our wind directions, we can see the wind here, and just the surfacing of the slab is interdispersing with the surfacing of the panel, but it does give us a good indication for each of the directions how the wind is applying. So positive, positive, and then high suction to lower suction coming off these. So the loading cases, I actually have them saved and I actually bring them in to make my life easier. So if I look at that for 1 second, there is an option to import loading cases from another file, so I can just go off and pull those from a typical frame. And I believe that there is a file that I have here that I can import, but I'm not going to import it today. Let's get on, do some analysis. So the last thing actually was we didn't set on our surface loading properties, surface materials. Looking at this here, we can see that we're codified, but if we look at the support here, we will see that we have a subgrade modulus of 30,000, so it's a stiff clay. It's still going to give us some problems, but at 30,000 is a reasonably stiff clay. On that, we also have we've freed this edge from this edge. We don't do it twice, so if we look here and we look at the releases, we've released it in all directions along this edge, so these two slabs are disconnected from each other totally. We don't need to do that disconnection on both sides of the slab, just on the one we want to consider. So hopefully I've already analyzed, and hopefully it will give me some results. So let's just go into results and graphical. And it's asking for an analysis. Luckily for me, this shouldn't take too long. It'll take about a minute on this frame, and you'll see the density of mesh that's been applied. Okay, I'm just looking at the questions here, and there's one about punching shear, and we can possibly look at that when we come back to the punching shear solution. So there's our dense mesh, and you can see it's an adaptive mesh that's got denser around hard points that we allocated. I decided not to allocate those as dense, but it always insists on having enough to create its mesh. And if we look at the shell elements and we look at the Y displacements, we will see that the Y displacements under all span service, this is all coming down considerably, and it's to be expected, and this is moving down further more than this because of the I'm trying to think of the right word, the spring stiffness of the soil. If I went back to align elements and just said give me deflected shape, you would actually be able to see how, with a magnification on it, there is a movement joint there between the two surfaces, just in there, because that's subgrade modulus, that's on the piles. We can also see that the slab is having awful problems under this stiffness here. So we will need to reinforce it and maybe think about not putting in a subgrade modulus. But a thicker slab, a stiffer slab is going to help us. And obviously this is all magnified out, so we're not that worried. So into design, I'm going to go quickly into concrete member design and concrete columns, and then we'll look at the slabs. So concrete members are all the edge bent members, and those attached beams were assigned to be the portion underneath the slab, but obviously glued onto the slab. So what you're seeing here is this small portion underneath, which I believe is 350 square. Yeah, 350, and then this is a 250 slab. So yeah, and you can see how it very simply does the design on these for you. Very straightforward and very simplistic. Your columns again are very straightforward, and in these cases we have big columns, and obviously we don't have much connecting them, and they're deemed to be quite slender because the slab is nowhere near the same thickness as the columns, and therefore doesn't count. So we need to get some more information. So let's look at the column data, and in fact it hasn't really designed it yet, so off we go, and it's suggesting 12s at 100. Now this is where we can actually benefit, because what we can do is we can turn around and say, well, actually maybe we didn't need a 400 column. We could reduce our column size down, say to 350 or 300, and see what happens. Obviously we're getting some problems with our links, and we're now getting problems with the spacing of the links. So we're going to take this down to 2x2 links, and we will probably get away then with only having one in each corner. So we can size down our columns as we decide, and we would then possibly say, well, let's take that down to 300 as well, and see how it goes with an auto size. 112s at 200, and everything is happy. So there's my two columns here, my edge columns designed. So I might dip back and change those in the analysis to be a smaller column than what was anticipated. Let's look at an internal column. This is a circular column. Let's take the lower one, and it's far too big. Whoever put this in was very not worried about space. So let's come all the way down to say a 300, 400 column, and size that up. So a 400 column is going to work fine. Come down to a 300 column and size that, and we would need, at this point in time, we'd need some extra bars, so we would consider pushing that back and auto size. That's better. 6 bars rather than having to go 7s, and 12s is all we need. So 350 at that. Would we get away with that? We would need to go up to 16s, 20s at the 300, unless we went up to 16s and put in another bar. There we go. So 16s was going to work. And again, we would then decide to change the same in here down to maybe a 300 as well. See what happens. And it's now giving us the same 6 bars at 1200. So that's your beams and your columns all being designed for you. And of course we can take these and we can send them out. In this case we got a little problem here just with the lapping of the reinforcement for the next span, which we can look at and take that, and there we go. And it's just saying no, I'm unhappy down here with these bars. That's better, and there we go. So we can work with our rebar and we can play with it. We can change our diameters, and we can even take the rebar from one configuration. So that's way over to the top. I believe 20s is going to be good enough. 2 20s, maybe 3 20s, and just go for a 3 bar arrangement. Pull that down and make that 3 16s. Normally you try and keep them all the same when you're doing this 2 bar lap, and I can then say let's copy that to the next span and see what happens. And we'll see with that then it gets a bit annoyed because it has. You'd really need to keep the 20s on both sides. And there we go. That now works. So 16s in the bottom, 20s in the top, and we are good to go. And that is a reasonable approach. You will notice, even though we're shallow on these beams, that they do have side reinforcement. And the side reinforcement is because when we look at our results, there is a degree of torsion in the from the slab automatically coming through. So that's your beams and your columns, and we can export those all out to AutoCAD as, for detailing, quite straightforward. I am a bit pushed on time. It's really about the concrete design. I'm not going to save any of the design change sizes because I don't really want to have to reanalyze everything. But that was what you would do in normal fashion. So, design, slab design. And I bet it's going to ask me to reanalyze anyway. No, we're in. Okay, we've got some information here. I'm going to get rid of most of it. And let's see if I have anything in here, and if I have anything in here. No. So let us look just at the first floor. So views, level 2, and here we go. There's the column coming from above, and there's the two columns going below. So we're going to put some basic rebar onto this. So very quickly add in a basic, and our basic will be 10s at 200, and it will be applied to this surface. So we don't actually know too much at the minute. I'm just going to quickly tell it not to bother giving me all that, so don't draw the mesh outside. And now when I go and say give me unity, areas, and I can look at any of the rain bar, and I can see now immediately it's the the hogging moments on these pile caps that are giving me areas of steel that I need to enhance on the top. Let's look at the bottom steel. YY and XX. So the XX is the steel running in that direction, and the YY is in the other direction. So that is your steel design, and it's telling me that 10s at 200 is actually going to work in the bottom, but in the top it's not going to work. So I'm going to go back out to my hogging area, and I'm just going to put in some top steel in here as additional steel. So I'm going to put some peak steel in, and I am going to put it in as one zone. It's going to be averaged not over the full width, but over an effective depth. I just go to my settings and just make sure that that's set correctly. So peak zones, symmetrical, one zone, and additional steel. Yep, basic rebar, auto design, grades, everything else looks fine. So now I can say we're 5, and I can say where. So let's zoom in and look at this, and we're going to say over this pile cap. And that's a pretty good guess. Now I do need, because there's an awful lot of calculations, just to redraw. And we'll see that the additional 10s at 200 is not enough. And it's not enough in both directions. Not by much, but it is not enough. So what we would need to do is come along and increase that to 12s. So it's okay in that direction, and then the other direction we'll see that we also need to increase this to 12s. So that's that one done. What I can now do I can copy this to zone 3 and apply it there. And I can apply it. Zone 2 is there. Where's zone 1? Did I have a zone 1? Looks as if it didn't apply zone 1. I'm just going to delete that one. So take this one, and I'm now going to copy it to here. And it's better if you look not at the Y or the X, but at both, and we'll see that it's actually working for both. There's tiny little variations here which are minuscule, and I would honestly say that you wouldn't consider extending the bars for those at all. So copy to there, copy to there. And you could even say copy to all of those. And they've all now come and aligned themselves to the other plane. I can actually take them one at a time and take this, and I can now say what's the problem we want to, and we want to, there is an alignment angle. Align column with beta, and I can say yes, and that might work. Or in this case, no, I'm going to say angle is 0. Now it's 30. So wrong direction. Try minus 30. And there we go. And I would just correct that one as well. And you can see at the moment that steel isn't working for those. It's actually asking for more because it's a wee bit annoyed. And I'm not going to go through and fix every single last one. So we now have this problem over here. And this is a classic example of a problem in slab design where we have walls supporting slabs. Because we really need to reinforce this. I can come along and put in a strip here. So I can come and say copy and apply it there. And that solved that problem. But it's not going to solve this area here, and I can go copy and solve that one. And in this case you might say, oh, I do need to extend that out a wee bit to make it bigger to cover that area, so you may want to extend that out. Now to solve this problem we have to think laterally. What we have to put in is a strip, and we're going to put a strip across here first. So apply, draw on this surface, sorry, and it's going to go from here all the way out. I'm going to take it a bit further out to here, but I'm actually going to take it out to here. So that additional steel is top steel. It adds to basic, it is top, and it's perpendicular, which is what you want. It's steel running in that direction. I now want to look at this area, and if I put an inclined strip, it's going to put that reinforcement perpendicular to the angle of the strip, which is going to be very clumsy, and it's going to force it down onto a third layer, which you don't want. So I'm this time going to add in another strip, and it's on this surface, and very simply this time I'm going to draw it from here, but I'm going to take it straight up to there, so that it is okay. It's overlapping a wee bit more in some respects than others, but it's in the right plane. It's a lot easier. I can zoom down and say, right, let's take this all the way down to here, pull it out to here, and that's it. Good. So that's that strip done, and those two strips are going to cover that. And if you take this one, this strip, strip 1, you'd actually probably take it out to there, and therefore you get the steel in both directions over that area. You won't actually have additional steel from the strip plus the peak zone. You get the stronger of the two. It does not add them together. It would only be one additional set of reinforcement. So that's in that area. Let's look at over here and let's go and slide in an additional basic steel onto this surface. So that's the surface I want. Yep. And now if I go and do a redraw, we'll see that in here, I'm just going to bring that into incline, we've got higher values. Bear in mind we're at first floor level. So we've got massive peaks over here. We're going to have a big sag here. So let's look at our sagging moments. And we'll see that we have massive sagging all over the place in here and here. So what this is telling me, particularly in the bottom steel, is I need heavier steel in this zone. And I might as well do it over the full area rather than over this area here and have very complex. So I'm going to come down and I'm going to leave the tops and look at the bottom steel. I'm going to put those up to 12s. Look at the bottom steel here and put those up to 12s. Now nothing happens here until we redraw this. And now we only get this one area here that we need to reinforce. So we can put a blanket reinforcement over here and possibly catch out this as well. So when you think about it, you're going to want to have some sort of rebar spanning between these two columns as a strip. So that's going to be your YY. So we're going to go from this column to this column as a strip. Add in the strip. And I'm just going to take this down to here. And I need to draw it. So on this surface. And it's going to be from there to there, and I'm going to widen it out. Yeah, I can go orthogonal if I'm really careful. And widen this out. So now I've got the strip. It's giving me, or will give me, no enhancement because the strip is first of all in the top by default rather than bottom. Adds to basic, and it's going to be top, and it's going to be parallel. So there we go, additional steel in that axis, but we still have not got enough. We're going to have a lot of extra steel in here. And I'm going to be guessing 20s. 20s is only giving me 0.976 as my utilization. So that big transfer slab axial load from the column here is giving us massive bending in that axis, which I needed to solve. So let's now look at the x-axis, which is the steel running in that direction. And I can put in some additional steel here and here to solve that. I can put it in either as a strip or a patch. So if I put it in as a peak, I can add it in here, and I'm going to put that bottom, and then that will solve the problem there. Now we've got two additional wee areas in here, and to be honest, it's getting so complicated that you might think about going back and reinforcing the whole slab, but that's not necessary. We can just work with a strip across here, add in another strip on this surface from here to here, and we're going to again make it bottom parallel, and just extra 10s at 200 is enough. So those additional little strips will be enough to solve the problems. Now, while you're looking at this, either this area or this area, you will have noticed that we don't have anything along the edges. That's because those aren't designed as part of the beams. They've already been designed for in the attached beams. So that makes our life so much more intelligent and simple. So that is that slab. Got all the steel at once, hopefully. So let's look at MRX. Obviously we didn't put in the top steel around these areas, and we can do so, if we wanted to. I'm going to leave them out just for the fun of it. And when we go to the sagging, we'll see that the sagging now works. And I just need to check. I think it's because it is taking the peak instead of the strip as being the critical. So if I went back to that peak, I would have to increase the steel in that direction to be the 20s. So it was in the YY, I think. Well, let's not guess, let's find out which one it is. Is it the Y? It is the Y. So direction 2 YY. Change those to the 20s in there as well. And they're now the same, and it's now harmonized, and it's all very, very good. So that's our design from a main steel point of view. The other half of the design, which is really fun in games, is the punching shear. And I always like to go into, and now what I want to look at is this punching shear. So going into punching shear, we can look at adding in punching shear to multiple objects at the same time, and we can add it into all of these as well, and we'll see they all give us our answers. Now we are on the first floor, so when we examine them we will see that these are the fancy end of wall punching shear checks, which are quite strict. This is on its own without any problems, so the rebar is giving us reinforcement that is quite good. At the edges here we obviously do need some rebar punching shear reinforcement, and if we look at something more onerous, something like around here, we will see it's a circular section, but on these rectangular square sections we have these bars, shear links coming in, and they're a wee bit skew, and what they are, they're equally spaced around the perimeters. So equally spaced on perimeter. I can also choose to go for a radial layout, which is a more common layout, and that will then give us our radial bars, and that is just like shear links or shear rails. We can add in 1, 2, 3, 4 legs at 155 centers to the correct depth, and we will have our shear links, all shear rails all ready to insert quite easily. We can also go for a even grid, which I don't like because we've got an even grid of 155, because that 155 is based on the effective depth of the slab. But our main reinforcement is at 200 centers, so there's a wee bit of a crossover there in information, and it's quite awkward to place. So the radial is more popular. And the last one is the cruciform. Now the cruciform would normally be just on the 4 cardinal points, but since this has got high shear, it's saying no, I actually do want links out here as well to enhance this area, otherwise I'm in trouble. So the cruciform nowadays is more commonly just the radial. And if we look at our circular section, you'll see that is default radial. It says equally spaced, but reality you would go for radial layout. Makes more sense. And likewise this one here, we'll make this one radial. One of the things we can do is we can just go in and grab a whole lot at the same time and ask them all to be. So that's your punching shear checking, and if you look at this one, for example, it is not seeing an opening near it, but if the opening was close by, it would then show up that as being a critical point. I know we haven't really looked at the top slab. If I go into the roof and I pop some basic reinforcement onto that, so just, yeah, that's on the different layer, add in a new layer and put in some basic reinforcement onto this and onto this. Then if we come to punching shear and look at punching shear on a top view, and we apply punching shear to this column, you'll see that it's taking that point out and it's taking this omitted out zone on the panel for the punch, allowing for the opening that's close by. So it does do all of those tricks in doing your punching shear. Now, if I was to drop down to the floor plan, these are all piled loads. So if I add in a piled set of information, we'll actually see that around this small wee pile head, we have a problem because the pile is only, I think, 250 square, 300 square, and it's punching around that. So we need to either put in some punching shear links or enhance that back up. So the only way to enhance that back up is to go and add in a drop. So let's take the thickness up by 100 mil and let's project this out by 200. So we've now got a 200 projection. That's an extra 100 mil thicker, and we'll see that both the outside and inside, so inside the drop's not thick enough, so we really need to increase the projection, say to 400, and increase the thickness to 150, and now we're okay inside, but we're still failing on the outside the perimeter. So what we're going to do is we're going to take this and we're going to push it on out. Let's try 500 mil. We're not quite. Let's go 600. Not there. I'm going to go 700, and that should be enough. So 700, that's 1400 total plus the 300 of the head. So that's 14, 13, 1700. So you could have gone 1725 or 725 and got a 1725 square projection. And that's another way of getting around the punching shear, is to give yourself localized drops. And if you've got pile heads, you can thicken those out to do so. And make that a solution for yourself. So we've done the main reinforcement, we've done the punching reinforcement. What we now want to do is to take this and push this out into AutoCAD. So I'm going to come back out to full frame, and I'm going to come back to basic and looking at some rebar. And there we go, our different layers all designed up. Naturally, we didn't complete the roof, so that's fine, and we actually didn't complete the ground as well. We're interested really only on that first floor. So let's go DXF or DWG export. Let us take first floor only, and let us take all the reinforcement including the punching, and we'll go for a load of AutoCAD, and we're going to export that. And here we go. For the bottom steel, we have this big area we need to enhance for the transfer slab, the big beam action in the slab in here. We've got heavy reinforcement in this zone than in this, so we went for 12s as the default rather than 10s, and that's in the X direction, and the Y direction is the same. When we move up to our top steel, we will see our zones of reinforcement that we have included. Bear in mind that this is for the steel running this direction, so we don't see the enhancement along here yet. And then we come down to the next one, and that is the reinforcement running that direction. And you might turn around and say, well, if this needs to be heavy, why don't we put this the same, and it's the 12s at 400, whereas this is 10s at 200. So we may decide to re-rationalize that to make our life easier. And then finally, looking at all the punching shear perimeters that we asked it to do, all the radial outputs, and for each of these zones that need punching reinforcement included. And that's your drawing done. Now, if we just step back, I'm not going to save that, and go back into the level 2, we can go and look at the rebar itself and see the rebar here. We can see the rebar, and we can see all the dimensions of the rebar, and we can actually even collapse this just to give ourselves a wee bit more room to work on this, and we can see the dimensions of these. And first of all, I look at dimensions, and then I look at the reinforcement. 12s at 200 here. These are 16s at 200. I need it a bit heavier. And this is down to 10s at 200. Well, you might decide just to make that at least the 12s at 200 to have a consistency around there. And you can rationalize that, and these need to be heavier for the awkwardness of the column corner. So you can rationalize your reinforcement, your size of your reinforcement, as well as the overall patterns, so that you have as few different patterns. So we can, as I say, take this one here, and we can go and say we want to make it 12s instead of 10s. And now it's the same pattern. And obviously that's for direction 1. For direction 2, we would probably want to do the same. So we would come down and also for direction 2 make that 12. So that's now all the same color scheme. And we can see our rationalization, and we can identify any areas you want to work on from a dimension or a size point of view. And that can be printed out just directly as a report, as well as to the DXF. So that is the main slab design covered. Very flexible, very detailed. What I want to look at is in more depth this pattern loading that we did. If I come and open another file and look at the pattern, so we've just got basic dead and live load, alternate loading. If I look at the load patterns, we'll see the 1 is going that direction, so it's the y-axis reinforcement it's trying to make worse. So maximum, minimum, maximum, minimum, and then the opposite in the other direction when we look here, and we'll see that. So that's those done. When I go into my results, if I look at my graphical results and I look at bending moments, that's only the columns, which is useful, but I'm after the shell elements. So let's look at the wooden armor moments, pop this into plan, and we will see that we're getting wooden armor moments around 80, 85. So let's place some values on, and let's put a value on, say here. We're getting 40s and 27, 28s. And this is on all spans loaded and 30s here. Now, if I go to this first alternate, which is max min, you'll see that we get a lot less, of course, but we get a lot more here. The values here are up to 48, whereas previously they were a lot less. So maximum, minimum, maximum-ish. Minimum, maximum's giving us horrendous sagging in the first spans, and that's quite critical. If you remember back to your student days, first span sagging is very high. It won't affect the hugging because that's based on all spans loaded. And then secondly, if we switch over to the alternative, you'll see that this has gone from 25s and 28s to 33s and 34s. So it's a 10, maybe even 15% increase in stresses. So that's the significance and the reason why we always like to consider the combinations of values. So ultimate cases, and we're looking at positive values, so we're looking at these positive values up here. If we then decided we wanted to look at negative values, and there we go, we've now got our negative in-span values coming up for us and saying our enveloped values of 46s and 32, 33s, 35s, remember they were only 28s originally. So that's just a little extra reason why we do this pattern loading in the program. So today we've looked at 3 programs. We looked at Master Frame, we looked at Finite Elements, and we looked at Concrete Design. In the concrete we've looked at the beams and columns and pile caps, but we've also looked then at the slab design. And they're all available as individual modules or bundled in together in things like the Building Design Suite. So please, thank you very much for joining me today. Any questions, just email them into either help@masterseries.com or sales@masterseries.com, and we'll be more than happy to answer any questions. Or if you want to take a free trial of the software, please do so. Thank you very, very much.